Yep.
Wonderful. Okay, we are going live. Hello everyone at home, welcome back to the Cambridge Festival from Cambridge University Astronomy. I'm here this afternoon with Dr. Nicole Pawellek, who's going to talk about something which is absolutely fascinating and I don't know much about, so I'm looking forward to learning all about the music of the spheres and the connection between music and astronomy. So over to you, Nicole.
Thank you, Matt. And thanks for inviting me for giving this talk. So in the next half hour or 45 minutes, I'm going to talk about music of the sphere. So the link between music theory and astronomy. And if you are joining live now, you are able to join our quiz during the talk. So you can just scan the QR code or you can go to the slido.com website and enter hashtag astromusic. And don't worry if this was now too quick for you, so the QR code will be visible for the first question. Okay, so what am I going to talk to you is at first a motivation. Why should we be looking for a link between astronomy and music? And then we need to talk about the basics between physics and astronomy and music theory so that we can understand each other and so that you can understand what I'm talking about. So this includes something like the Pythagorean scale, which is basic music theory, which we still use nowadays. And of course, then a quick guide to musical notation, so how a music sheet is written. So then we come in the fifth section to the early theories of astronomical harmony, then the Keplers laws, and then a final, let's say, a fun section for the end of the talk. Okay, so let's start with the motivation of why are we interested in music of the spheres. And there I have to start with the old Greeks. And for those old Greeks, music was much more than it is nowadays for us. So they believe that music is the embodiment of all harmonic dimensions. And this includes three different kinds of music. So the first kind is what we know as music, the musica instrumentalis. So this is the harmonic dimensions of making music with instruments. So including your voice and strings and whatever. So the second part is the musica humana, which is the harmony of the soul, the harmony of the body, and the harmony between soul and body. And so this sounds a bit more esoterical, but I think we can agree that when listening to music, we feel good. So at least that's kind of the motivation for the second kind. And the third kind was by far the most important sort of music. So it was the music of the cosmic dimensions, the musica mundana. So this was the dominant role up to the medieval centuries. So, and this was even the basic of their cosmological model. So how the people in the medieval saw the universe working. So in a picture of that you can see here. So this is actually, it looks a bit more difficult than it is. So we will go from the inside here to the outside and analyze the spheres we see. So the first one is, of course, the Earth. So because the people in old ancient times thought that Earth is in the center of everything. So we are in the center of the universe. So, and then the first sphere, so here it's called Luna. So this is the sphere of the moon. And then going up further, so we have on the sphere here, so this is the fourth sphere, we have our sun. So, and then between moon and sun, we have Mercury and Venus. And then from spheres 5 to 7, we have Mars, Jupiter, and Saturn. So this is basically, the ancient view of our solar system. And now it becomes a bit more, strange. So at first, not as strange. So it's the sphere of the fixed stars, which was introduced by Plato. So saying that all the stars are fixed in this sphere. And then the ninth sphere is the so-called crystal sphere, which is derived from Genesis. So this is a part of the Bible. So in this ninth sphere, it was the home of all the saints. So, and the ninth sphere was also the reason why all the inner spheres, like Jupiter sphere and Venus sphere, are moving. So they are basically rotating around each other. So the 10th sphere is the so-called empyrean. So this is the sky or the heaven of light. And this is the home of God and all the angels. So you see that people in the medieval, they combined all their religious beliefs with what astronomy is telling us. So now we have to come to the basics. So there's a motivation between music and astronomy from history. So, but first of all, we have a big problem, and this is the following. So music theorists don't understand anything about astronomy, or in this case, rocket science. And the second part is rocket scientists or astronomers are not very good at understanding music theory. So therefore, let's go to people like him. So this is Brian May from the band Queen. So he is, of course, a famous musician, and he has a PhD in astronomy. So we need people like him to understand the physics or the astronomy and the music part. So and hopefully I can follow up with that and can explain something to you in the next couple of minutes. So let's come back to the model I showed you some seconds ago. So this is the medieval cosmology model. So now we make a schematic model of that. So this is the same, basically, what I showed you in the other picture. So we have the Earth in the center. So this is the so-called geocentric system. So it's basically that people believe that everything was orbiting around the Earth. So we are in the center. So it's a kind of a political worldview. So politicians might see that. I mean, you can swap just the letters in the beginning. So it's an egocentric system or a geocentric system, if you want it like that. So, but then, of course, later came the so-called heliocentric system. So there we changed the system to that the sun is in the center and Earth and all the other known planets are orbiting around our sun. So we have Mercury, Venus, Earth. So, and then the moon is orbiting around Earth. Then we have Mars, Jupiter, and Saturn. So and if you're missing the other planets, so they were not known at the time we are talking about, so the medieval. So the other planets come in later. So but now the point is, why do we differentiate between the sun and all the planets orbiting around? So the sun is a star, but what is a star actually? So it is a massive luminescent celestial body made of hot gas and plasma. So much for that. And to get a better impression on what our sun is, for example, in comparison to other stars. So here on the left side, we see a blue giant. So it's big, it's blue. Yeah, astronomers don't have a huge fantasy for that. So it's blue, it's giant, so it must be a blue giant. On the right side, we can follow up. It's big and it's red, so it's a red giant. So in the center here of the image, this is actually our sun. So you see it's quite dwarf-like compared to these giant stars. But our sun is by far not the smallest star. So here in a small red thing, you have it's small, it's red. Obviously, it's a red dwarf. So in here, an example for that is the star Wolf 359. And if you're a Star Trek fan, you know, of course, Wolf 359 is a very important star because this will be the place where the Borg will enter the Federation. Okay, so much for that. So now we know about all the stars and the star sizes, but now what is a planet? Why are they orbiting the stars? So first thing is a planet is a celestial body. So a body that is in the sky, of course. Okay, great. First part is which possesses an orbit around the sun. Okay, so for the planets in our solar system, that's great. So because they are orbiting the sun. Second point is which is of spherical shape approximately. So, okay, so all our planets are near spheres, as we can see from the nice images. And the third point, which is actually a very important point, is that it is dominant object on its orbit, meaning that it cleared the orbit from other bodies due to its gravitational field. So what does this mean? So it means that planets are quite loners, let's say. So they're orbiting alone on their orbit. So they are not crossing paths or sharing their space. So and this is basically the reason why we excluded Pluto as a planet from our solar system. It's because Pluto didn't clear up his space. So Pluto is sharing its space with a lot of other objects. So, and for the children out there, you see astronomers can punish you if you don't tidy up your space. So therefore, clean at home. So if you want to become a planet. So summarizing our solar system, we have our sun here on the left side, and we have Mercury, Venus, and then Earth as a third planet. And the distance between Earth and the sun is usually, or is an average distance called the astronomical unit. So this is a very important unit, and it is 150 million kilometers. So that's a very big number. So you see all the zeros here. So it's very big. So, and our Earth in comparison to the other planets, you see as well, it's quite small. So we have a large distance already from the sun, but we are not as far away as other planets, and we are by far not as big as Jupiter, for example. So much for the astronomy at first. So now we have to come to a bit more physics. So what is a tone? Because we want to talk about music, so we need some kind of terms. So a tone is a simple vibration of a body. And what is a vibration of a body? For example, a pendulum. So please don't look too closely to that. I don't want you to get mesmerized, but this is actually a simple vibration. Second point is, what is a sound? A sound is the sum of several tones. So this is what a musician is actually calling a tone. So because when a musician is making a sound with an instrument, so it's already the sum of several tones. And thirdly, a noise. A noise is a chaotic vibration, so we can't hear any specific tone to that. So it's kind of this noise from the waves from the ocean, for example. So now we clarify what is a vibration, and now the point is, what is an elastic body? Because only elastic bodies can make music. So elastic bodies are, for example, strings. So violin strings or guitar strings, or even a piano has strings. Bars can also make music, so like the xylophone or the glockenspiel, and membranes like the drums. So you're hitting the drums and then they are vibrating. And of course, air in pipes like recorders or organ pipes also vibrate and make sounds. So now we know what is making sounds, we know what is a sound. Next point is, now we can come to the music theory part. So now let's start with the Pythagorean scale. And Pythagorean scale, because it is based on the old Greek Pythagoras, who was doing experiments with a so-called monochord. And a monochord you can see here in the center of the image. So it's a huge, or it's a block of wood. So a massive piece of wood. And what you do is you fix a string across it. And what Pythagoras was doing is he compared the length of the different strings to each other. So he was fixing two strings to it. So I hope you can see that a little bit. And then was investigating how to divide a certain string to get special harmonies out of that. So, but before we go further, so now the point is, I don't have a monochord. So now we want to investigate these experiments which Pythagoras did. So, and since I don't have a monochord, so there's a paucity of monochords in Cambridge, I will just do or use my violin. So just wait. So that's here. And the first thing is, we want to investigate the pitch of the tone. And the pitch is, how high a tone is. So, and the point is, that's a certain pitch. So if we change the pitch, we have to change the length of the side. For example, so hopefully you could see that. So it means that the shorter the side is, or the shorter the string is, the higher the pitch. So we can do a similar experience with different strings. So we can analyze the harmony actually. So this is what Pythagoras did in the second step. So after defining the pitch is proportional to 1 over the length of a string. So we can do it with different strings. So for example, so this sounds rather nice, but we can have different harmonies. So these all sound rather nice, but we can also have some very awful sounding harmonies. So these are nearly hurting the ears. So therefore, yeah, always be careful when practicing the violin. But what we get out of that is that there's an interval. So this is the so-called the ratio between two tones. So and the ratio between two tones is the ratio between the length of the different strings. And doing all these experiments, we can find out that there are special harmonies. So what I showed you a couple of seconds ago is that there are certain ratios between the strings that make nice sounds, and then there are certain ratios which sound just awful. So, and the first question for our quiz today is, what are these ratios? So I give you certain ratios of the length of the strings, and I will give you a couple of minutes to decide what are special harmonies. So you can just give in one answer, but it will be quite interesting to see what you think is the ratio between different strings. So so the first answer is coming in. So we have special harmonies. 1 to 2, 2 to 3. That's great. So I will give you a couple of minutes for people to get their smartphone ready. So just scan the QR code or go to slido.com and hashtag astromusic. 3 to 4. Okay. Just keep going. I will answer this question so in a couple of minutes. So when people actually did a bit more answering. 2 to 3. Answers coming in. That's good. That's quite interesting what you believe is a special sound. 2 to 3 seems the thing. So far nobody was going for 15 to 16 or 45 to 32. So I'm not sure why. Probably you don't like those numbers, or they look too awful to be a special sound or special harmony. So I will give it another let's say 10 seconds. And then I will answer what are the special harmonies. So, but obviously you prefer the 2 to 3, which is fine. So, okay, I can tell you all the answers are correct. So all the answers will give you a special harmony, which sounds more or less nice on a violin if played correctly. So, but for now, we will focus on the special harmonies 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Okay, so, but these are all numbers. So, and if we have the numbers, so, but what is actually, which ratio, what interval? So, because if we do music, then usually we don't think about ratios of lengths of, string length or something. So we are actually thinking of terms like a fourth or a fifth or an octave. So therefore, now we have to investigate which interval is which ratio. So in there, the easiest way is not looking at the strings, but looking at a so-called piano keyboard. So this is a piano keyboard. So in there we see we have white keys and we have black keys, and the black keys are organized in twins and triplets. So, and we start with the white keys. So for the moment, we just ignore the black keys, and we're looking for the distance between a key below the twins and then to the second key below the next group of twins. So, and this is actually the octave. So this is a ratio of 1 to 2. So the pitch of the second key is exactly twice as high as the pitch of the first one. So then we can go further. So why is it called an octave? So if you count the white keys, it's 1, 2, 3, 4, 5, 6, 7, 8. So an 8 is the word octave, just from the Greek language. So this is rather easy. So we can go further then. We can just investigate the next ratio. So this is 1, 2, 3, 4, 5. So and therefore it's called a fifth. So we have a ratio of 2 to 3. Then going further again, so now we have just 4. So it's a fourth with a ratio of 3:4, and so on. So there we have a third with a ratio of 4:5. So this is the simple start. So, but what we didn't investigate now is what is actually the ratio between a key and its neighboring key. So what is the smallest distance, or what is the smallest ratio? And this you can easily do. We can investigate the difference between a fifth and a fourth. So because, we have a fifth with 5 white keys and we have a fourth with just 4. So we can calculate that. So this is basic maths. And then we get that this is a so-called second as smallest unit on a piano. So here we see it's the distance between those two keys, for example. So, and it has a ratio of 8/9. Okay, so now the idea would be we take these 8/9 and we can just put several 8/9s or multiply them to get all the pitches correctly on a scale. But the problem is this is not working that well. So of course, for the first thing is if we press the same key, then of course we have the perfect tuning. That's true. And it's working for the second because we just defined it as this point. But if we go a note higher, so if we go to the next key, so this is then called a third, so which should have the ratio of 5/4, as I just told you. And then, but then comparing it to 2 seconds next to each other, we get that there's a rather large difference. So, and this difference is called a syntonic comma, because so these two seconds next to each other can't reproduce a third in a very good way. And if we go any further, then we see that it's also awful for an octave. So we see that what we need is a value of 2/1, so to get the pitch twice as high as for the basic tone. So but what we get is that there is a significant difference, and this is the so-called Pythagorean comma. So and this is a reason why making music is quite difficult for string players, so violin players, compared to piano players. So it is important that this is not working, and that was a problem to compose in different scales. So for example, so some of you might know we have C major scales, or we have a D major or a G major. And due to these differences, it was not possible to play an instrument in different scales. You had to decide which scale you wanted. So the problem was just because we wanted to divide our octave in equal sized steps, and a reason was that the Greeks, for example, didn't know about irrational numbers. So here we come back to mathematics. So the problem is rational division leads to the forgery of the intervals, as I just showed you. This is so-called a wolf fifth. So it just sounds awful, like a wolf howling to the moon. Then point was we had to make some progress in science, so in mathematical science, because we needed to introduce power laws and logarithms to get to the idea how we could divide an octave in steps. So in here we have some paper working on that. So Michael Stiefel was the first one to recognize the meaning of the logarithms in case of music. And why do I mention him? So this is just a point of local patriotism. And the second point is that the first calculation of logarithms was done by an instrument maker as requested by our famous astronomer Johannes Kepler. So astronomers are usually very strong connected to music and astronomy, of course, but they actually found out that the logarithms just invented or just discovered by maths are very important to either music and astronomy. Okay, so now let's just do a little bit of musical notation stuff. So this is rather short. So first thing is we have our lines of stuff, and they give us the pitch of a tone relative to a key note. So they just give us the relative pitch of a tone. As I said, so we can't say anything about the actual pitch by not introducing a so-called key later. So what we see is that the difference between the pitches is a prime, a second, a third, a fourth, a fifth, a sixth, a seventh, and an octave. So this is our scale. So now, next point is only the clefs give us the position of the keynote. So, and these clefs are called, for example, the G clef, or you sometimes call it the treble clef. Then we have an F clef and so-called C clefs. So why is that? Because they define this specific note on the staff. So for example, here we have a G clef in the line below. So, and this is encircling the note G. So when we look here in the middle, so here we see this is G, and this G clef is just encircling it. And it's the same thing for all the other clefs, giving you the keynotes for the specific lines of stuff. So what we also have to introduce is the special signs, like a sharp sign and a flat sign, and a sign to resolve everything. So this is because we need to introduce the black keys at some point. So A sharp leads to a semitone higher, and then we have B flat. So flat goes a semitone lower, and the resolution sign just turns back to the main keynote. So much for that. So let's come to the early theories of astronomical harmony. So let's come back to the geocentric system. So let's remember, so Earth is sitting in the center, and everything in our solar system is orbiting our Earth, including the sun, including the moon, as we can see here. So, and the first thing about music of the spheres was the so-called Plato's music of heavens. So, and this was connected with the story of creation of Earth. So this was given in a so-called creation by Timaeus. And so we are now talking about how the Greeks viewed how the world was made. And the idea was there was a creator, and this creator generated or produced a sphere. So because a sphere was thought to be the perfect body, so and this sphere was rotating around itself because this was the perfect motion. So and then the creator generated three different sorts of materials. The one was the being, the other one was the same, and the other thing was the different. So, or the difference. So it's these three materials, and then he was creating, or they were creating, the square numbers and the cubic numbers. And with the square and the cubic numbers, the creator was generating or mixing the materials in certain ratios based on these square and cubic numbers. So and if we put them together, so from a Pythagorean point of view, this sequence of square and cubic numbers is the most important thing to understand the structure of the world. And it gives also the basics of music theory. So for example, what the creator developed there was the harmonic and the arithmetic mean. So thinking back on mathematics in school. So let's just take the numbers 1 and 2. And we have the arithmetic mean. So this is an easy thing. Here, it's A plus B divided by 2. So if we use the numbers 1 and 2, we have 3/2. And this is actually the ratio of a fifth. So if we do that same for a so-called harmonic mean, this is 2 times A times B divided by A plus B. And if we use the numbers 1 and 2 again, we get a value of 4/3. And this is actually a fourth. So much for that. So this was the most important evidence for the Greeks that music and maths and astronomy are connected to each other. So going further, the creator created different spheres within this main sphere at first. So it was divided by exactly those ratios given by the square and cubic numbers. So and this is actually the first view on our solar system. So the creator, or Plato, was thinking that the distance between all the bodies in our solar system, so the moon, the sun, Venus, Mercury, have a certain distance to each other. And this is based or given by the square and cubic numbers. So here given is 1, 2, 3, 4, 8, 9, and 27. So and then, but we don't know what this is actually, what distance it is actually. So they just know it's a number of 1, whatever. So and then we can compare the ratios between the numbers. So here the ratio between the sun, the distance of the sun to Earth and the distance of moon to Earth. So we get something like 2/1, 2/1. And this is an octave. So if we go further, then we get 3/2 for Venus to Sun. So this is a fifth. And going further again, we have Mercury and Mars and Jupiter and Saturn, and all of them produce a kind of interval. So we have fourth, octave, second, and octave plus fifth. So if we put that together, and what I recently told you in a line of star with certain keys. So going from very low, so this is a so-called bass clef, for example. So very low to, and here we have the treble clef again, to a very high note. Then we get something like this. So I will play it again. So it sounds a bit strange, but it was the first idea on how our solar system was built or produced. So there we have different intervals, and if we put them together, it was the first harmonies of the spheres. And nobody said that the harmony of the sphere must be pleasing for a human human ear. Okay, so much for the first attempt on astronomical music. The second attempt was more a technical issue. So it was the Planetary Scale by Nicole Pawellek. So, and this was based on the idea that the Greek lyre possessed 7 strings, or it still possesses 7 strings. And in the solar system, there were 7 known planets. And Nicole Pawellek said, this can't be a coincidence. So we have 7 strings and we have 7 planets. They must be connected. So, and a Greek lyre looks like this. So, and if you want a little bit more of a modern kind of thing, then we have here Mr. Spock playing different sorts of lyres. But anyway, so we have 7 strings, and the way it is carried by the player is that you have a string closest to your body and you have a string farthest away. And this is remembrance on the distant planets. So for example, we have the highest note, which is Moon, because it's closest to the player. And then we have the lowest note, which is Saturn. And this is because, the string here is farthest away. So if we put that together, then of course we get a scale. So, and this is the first so-called planetary scale. And for the musicians in the audience here, why is there a B flat written there? So this is so-called tetrachord or shared tetrachord E to A and A to D dash. So, and this is based on the hypophrygian mode on finalist A. So all the people who are not musicians or firm in, experts in music theory, you can just ignore it. I will not mention that thing again, but just for the interested musicians here. So much for ancient times. So now let's travel further in time. So let's come to Johannes Kepler. So because he was one of the most famous people doing research and harmonies of the spheres. So, and now we are changing from the system of geocentric solar systems to the so-called heliocentric system again. So which was introduced by Nicolaus Copernicus in medieval times. So what Kepler did now, so we have the sun in the center, and now we have Mercury, Venus, Earth, and so on orbiting the sun. And point is that now he tried to derive the distance between the planets. So what he did was a so-called polyhedral theory. The idea is planets move through something like air, and since they do that, they produce a sound. So like the string of a musical instrument. So you should hear something. So and the speed of the planets is inferred from the polyhedral theory. So what is that is given in that image. So this is kind of a very strange thing to do. But anyway, he did it. So let's assume here the outer sphere, so the outer ball here. This is the actual position of Saturn. So and then Kepler was putting in a cube. So and this cube had certain dimensions. And these certain dimensions led to that a sphere, which just fits into this cube, must be the distance of Jupiter. So, and his idea was he had to investigate all these different polyhedras, like a cube, a tetrahedron, or a dodecahedron, and so on. So it's not getting easier. So the cube is by far the easiest body by that. So he put that in there, and then to define or to infer the actual size of the sphere where a planet is moving around. So what he got out of that by calculating a lot of things is that he got speeds with certain ratios given here. So we have 3, 4, 8, 10, 12, and 16. And again, nothing is mentioned here what kind of unit this speed is in. So, but what we get out of that is comparing with the planets. So here we have the speed 4/3, or the ratio between that. So we have a fourth, an octave, a major third, a minor third, and a fourth again. So and this sounds like this. I play it again. Yeah, so this sounds much nicer, so much more, let's say, pleasing for us, but still it's kind of a very strange thing he did. So and the point is, just imagine, so he was trying to publicize or publish a new book based on this polyhedral theory. So in 2 days before he submitted his manuscript to the editor, he discovered the famous third law. So giving the actual equation on how to calculate things. So he changed within 2 days the complete manuscript from this polyhedral theory to the actual mathematics we still use nowadays. So just imagine what kind of effort that has to be. So and therefore, let's go start with the first law, which he discovered in his 20 years of research on this polyhedral theory. So and the first law just says that planets move around the sun on an ellipse. So and this ellipse has 2 foci, and in one of this foci, the sun is situated. So and just to get you the correct terms there, we have the so-called semi-major axis, which gives you the distance from the center. So this is the first law of Kepler. So just saying, okay, the planets move on ellipses. So the second law is the so-called area law, which says that a line joining a planet and the sun sweeps out equal areas during equal intervals of time. So this is basically saying that when a planet is coming closer to the sun, it's faster, and when a planet is far away from the sun, it's slower. So that's the basic idea of this area law. So now the famous harmonic law, which changed everything, is that a mathematical description I wrote down here. So because it's just the easiest way to understand it, but let me explain in more detail. It says that the squares of the orbital periods. So this means orbital period is the time one planet needs to surround or to orbit the sun. So this is the time T1 and T2, and we take it squared, and they act like the cubes of the semi-major axis of their orbits. So this means what we can tell by that law is that a planet closer to the sun in general is faster compared to a planet farther out from the system, and exactly following this equation given here. So based on that, Kepler was looking for a lot of harmonies in the planetary system. So, but where should he look for harmonies? So we can look for distances to the sun. We can look at periodic times and true daily path, which is how far is the distance a planet travels on a day, or angular motion, which is nothing else than speed. So what he did at first was looking at planets' distance from the sun again. So in remembrance of the old Greeks. So, and then what he did is he assumed we have an ellipse. So we have the sun in one of the foci, and we have a planet. So in this planet, of course, since it is an ellipse, we have a closest distance to the sun, which is the so-called perihelion. And we have a farthest distance of the planet, which is called aphelion. So then he introduced a second planet, and for which we can say exactly the same. And now we have 2 special cases comparing both planets to each other. So we have a case when the outer planet is closest to the sun, while the inner planet is farthest away from the sun. And of course, now we can do the exactly opposite case as well. We have the inner planet closest to the sun and the farthest planet, or the outer planet farthest from the sun. So then we compare the distances in these special cases. So let's start with Jupiter and Saturn. So in the first case, shown in blue, we have Jupiter closest to the sun and Saturn farthest from the sun. So what we get out of that, if we compare the distances, is a ratio of 1/2. This is an octave. So in going to the second case, which is shown in yellow or orange or whatever, is that now Saturn, the outer planet, is closest to the sun and Jupiter is farthest from the sun. So there again, we get a special ratio of these planets, which is 3/5. And this is the interval of a major sixth. So now he did it for all the planets known at that time. So Mercury, Venus, Earth, Mars, Jupiter, and Saturn. And my next questions to you is, what do you think he found out? So did he found, so how many planets were actually showing harmonies like Jupiter and Saturn? So I will give you again some time. So now we had 2 planets showing these harmonies. So now we can have 3 planets, 4, 5, or 6. So at that time, we only had 6 planets. So were Mercury, Venus, Earth, Mars, Jupiter, and Saturn. So therefore, are all planets showing these kind of harmonies? Or are just 3 planets showing these kind of harmonies, or 4 or 5? Yeah, so just make a guess. So I will tell you the solution to that question, or the answer to that question. Yeah, okay. So you say all known planets show such kind of harmonies. Why not? I mean, it might only be 5 or 4 as well. So we'll give you a bit of time again. So just scan the QR code or go to slido.com and #astromusic. Yeah, okay, 3 planets. Okay, we'll give you 10 seconds and then we go on. Okay, so you think all of the planets show harmonies? Yeah, why not? Because that's completely true. What we found out is that all the planets really are in these certain proportions of intervals. So the white ones were proposed by Kepler. So we have octave, major sixth, double octave, octave plus a fifth, and so on. And here I added in blue other intervals. So this is caused by the fact that Kepler didn't know about the well-tempered scale. So which was the idea of avoiding the Wolf fifth, so like the fourdering of intervals. So, and if we apply that, then we go nearly perfectly with a fourth and a tritone and a fifth again. So it really shows that all the planets have these certain harmonies between them. So which is quite impressive. So from a statistical point of view, we would expect perhaps 3 or 4, but not that all of them have that. So then Kepler was also looking at the angular motion. So he was using the speeds of the planets and having a bit of fun. So he said, okay, a certain speed is connected with a certain pitch or a certain note in that case. What he found out is, or what he was using was the ellipse again and saying, okay, in a perihelion, our planet is faster, and in the aphelion, it is slower, just based on the second law he found. And then he introduced the planetary scales again. So he said, okay, a certain speed, a faster speed is a higher pitch, and a lower speed is a lower pitch. And then he did that for all the planets in our system, and he was comparing it with the so-called ecclesiastical scales. So ecclesiastical scales were used at that time. Kepler lived as church music, and so he was doing science connected to religion at that point. So many people did that at that time. So and he found that certain scales were attributed to certain planets. So, and these are the names of the scales, so don't bother to memorize all of them. The most important one is, of course, for Earth here, and it's called Phrygian mode. So in this Phrygian mode, he argued that, of course, because this Phrygian is a very miserable sounding scale. So it is connected, for example, to music churches play during Lent time or in Lent terms. So it's quite sad music and miserable. And Kepler's idea was, of course, because life on Earth is miserable, so we must have this certain ecclesiastical scale. So now I can imagine that most of you don't know what a Phrygian scale is. So let me just introduce that. So here we have the piano keyboard again, and the C, and we play a C major scale. So we start with the key below the black twins, and we go up to the next key below the next group of twins. And all of the keys have a certain arrangement there. So we have a semitone. So this semitone is where we have no black key. And so this is in a scale from C major on the 3 and 4th part, and between the 6th and 7th part, 7 and 8th part. So now the idea of the Phrygian scale is just we shift everything to the and start with the key of E. So here we know now that the semitone is between the 1st and the 2nd, and between the 5th and the 6th. So this changes the whole harmony of a piece of music. So you, if you have free time, then you can just Google pieces in Phrygian scale. So they sound quite sad, as I said. Okay, so fun fact: Kepler was looking at periodic times of planets as well. But what he said is there aren't any harmonies in planetary periodic times. But the funny aspect from that is that astronomers nowadays actually find these periodicities. So for example, the Galilean moons of Jupiter. So here we have Jupiter in the center, and we have the moon Io in the closest moon to Jupiter. And when Io is moving one time around, of course it's 1/1, and 1/1 is a so-called prime interval, so pressing the same key. And compared to the next moon, Europa, so Io is going around Jupiter 2 times, while Europa is just going around once. And then again, Ganymede is the farthest moon in this plot. So, and Io is going around 4 times, while Ganymede is just going around once. So this is more or less, exact ratio between that. And these are, of course, octaves. So, and astronomers do a similar thing for our solar system. So in there, let's come to a very interesting plot astronomers find quite amazing. So here assume our Earth and Mars and Jupiter on the other side here. So and in between Mars and Jupiter, we have the so-called asteroid belt. So these asteroids are arranged in a belt around it, as I said. And now what astronomers do is they count all the asteroids at certain distances. So they say, okay, we look all at 2 astronomical units. How many asteroids do we find there? Then we look at 3 astronomical units. How many asteroids do we find there? And then we generate an actual plot. So it means we count all the numbers and then say how many did we find. So in this plot is exactly showing that. So we have here a high number of asteroids. So here it's around 300 asteroids on, let's say, 2.35 astronomical units. So then we go along, and then we see a certain gaps in between. And these gaps are actual ratios of distances with Jupiter. So I showed you just the moons, they're going around 3 times, and then while the other moon is going around once. And this is exactly the same. So here in this case, we compare the position of the asteroid with the position of Jupiter. So for example, here in the first point, which I show you here, which is an actual octave and a fifth, is the asteroid would go around 3 times, while Jupiter is just going around the sun once. So this is the same for all the other aspects as well. So we have a ratio of 5/2 again, so where we don't see any asteroids. And this is actually, so an asteroid would go around 5 times and Jupiter just twice. So, and if we go further, so doing a lot of music scales here again. So here we have an octave and a major third, 7/3. It sounds a bit out of tune for that case, but it's close to an octave and a minor third. And of course, here we have an octave. So now there are other areas. So if we include all the other scales, we see here there is the octave and a fourth. And then we have here a major second. And here we have the minor second. So what you see is actually it's a scale going on. So we have the octave starting from the right. Then we have a minor second, a major second, a minor third, a major third, a fourth, and a fifth. So this is a perfect asteroid belt scale. So this is and very much seeing in the distribution of asteroids in our asteroid belt. Okay, so much for science. So what astronomers did is where they had a lot of fun, and they made this nice video of a famous planet, Trappist 1. So or star Trappist 1. And what we see is the actual pitch of the tone compared to the distance of the planets. So much for that. So this is, actually it sounds a bit out of tune, but it's quite fun to investigate stellar systems with 7 planets found in that. So now let's come to the end of the talk. So I will just introduce some great astronomers and musicians investigating or working on so-called harmonies of the spheres or music of the spheres. And first of all, we have our famous Friedrich Wilhelm Herschel, so discoverer of the planet Uranus. So he was an astronomer and a musician. So he was composing a lot of symphonies and concerts. And he was, as I said, a famous astronomer as well. And then next point, this is actually his sister, Caroline Lucretia Herschel. So she was helping him at first with his astronomical observations, and she was an accomplished concert singer. So then she became famous for a lot of stellar catalogs and discoveries of comets. So the third point, a third person is a woman again, because we need to emphasize how many great women did actually work in astronomy. So and this is actually a princess from Germany, and she was doing compositions and actual calculations of positions of comets and asteroids. So she was corresponding with mathematicians like Gauss, for example. Unfortunately, nothing of her compositions remained over the time. But anyway, so here this one is a famous guy I think that everybody knows at home. So this is Mozart. So he didn't actually do any astronomical things, at least I don't know any of that. But what he was doing, he was composing the famous Jupiter Symphony. So he was at least doing some research on the history of Jupiter. But another guy inspired by astronomy as well. So this is Gustav Holst, and he was famous for his suite on the planets. And then a very famous guy, you probably don't know him, but he composed one of the famous melodies. We all know it, and that's that one. Yeah, hopefully you all recognize the melody. So this is Alexander Courage, who composed the famous Star Trek melody. And now I will finish the talk, so I kept you from your nice afternoon already, with this nice 51 Pegasi musical.
First was a world round an old pole star, that's true, but the news is a sun-like star with baubles so quick and precise to be designed. No fluke, not a spot, if you like it hot, you're gonna love this find. Pegasi 51b, planet discovered, orbit traced every 4 days, hot as can be. Its order, Jupiter size, was something of a surprise, especially given its star's proximity. Pegasi 51b, it's a new pair of meteors, exoplanets, soon they'll be free. As planet falls on its sun, it shifts the stellar spectrum. That's how we got the syntonic legacy.
We got your funding, we got your funding. It's treacherous, so treacherous.
On this new breakthrough feels Monday.
Proof of the truth I've been telling you.
This is so mean anomaly. Pegasus, Pegasus, Pegasus.
51B planet uncovered. Round the 4 main sequence star, spectral type G. We know its mass to be high. Half Jupiter by sun eye.
It's 50.6146 for woman. It shakes her faith and how planets are formed. It's stars and Pegasus, leaving an egg, and thus living the planet as B50. One Pegasus.
Okay, and with that, I thank you very much. I hope you enjoy the ideas of astronomical music and musical astronomy. And I'm now open for questions.
Wonderful. Thank you so much, Nicole. That like 51 Pegasus B Aladdin song brings me so much indescribable joy every time I hear it.
Yeah, they are great. Yeah.
It's just like pure happiness. I love it. So I can see a couple of questions on Slido. If anyone has more questions for Nicole, you can either use Slido or you can pop them in the YouTube chat. Can you see the questions on Slido, Nicole?
I can try. Yeah. So you can start with the questions on YouTube, perhaps.
So far there are no questions on YouTube, but there are a couple on.
Okay. Yeah. Sorry. Yeah. Okay.
So yeah, if you want to do the Slido one, or do you want me to ask you? I can read them to you if you want.
Yeah, that would be cool. Yeah. Just yeah.
So first of all, Andrew wants to know: do you use harmony in your research? Like you've been talking about this idea of harmony a lot. Is that something that relates to the work you do, or is it just for fun?
Let's put it this way. So astronomers use harmonies not in a musical sense, but just in the ratios of numbers. So I do asteroid dynamics and stuff like that. So if we get a ratio, it's 2/1, then it's just a ratio of 2/1, but not thinking of an actual octave of that. So I was quite amazed when I saw this great plot on these asteroid gaps in our solar system and seeing, okay, it's an actual scale, what we see there. So I think that many astronomers know the numbers, but they don't connect it to music theory. So it's not a real thing.
Yeah, it makes sense. And we have a question from Fangdar May, who wants to know, does Holst's The Planets relate to the music of the spheres at all?
No, I don't think so. I think it more connects to the history of the actual gods of the name givers of the planet. So because Mars is the bringer of war, for example. So this is the actual title of the piece. I mean, if you like, for example, the Lord of the Rings, the music of Lord of the Rings is based on Gustav Holst, the planet. So they are quite familiar, but there is no actual harmony of the spheres in it, as far as I know, but perhaps there are musical experts out there who know better.
Wonderful. Thank you so much. That looks like all the questions we have, I think.
Okay.
So yeah, thank you everyone at home for listening. Thank you to Nicole for that absolutely fascinating talk. It's always really lovely to see the connection between these two different intellectual spheres, right? And you realize that a lot of these things that we think are very separate have these deep connections, which reveal things that we might not think might be there.
Yeah.
Wonderful. Yeah. So Nicole, thank you so much, and thank you everyone for listening. As I said at the start, this talk has gone out as part of the Cambridge Festival, and all week here on our Cambridge University Astronomy YouTube channel, we're going to have all kinds of fantastic things. So every day at noon for the next week, we have crafting activities for children, including making your own planets and baking galaxy cakes. We have a series called Black Hole Wars, which is getting into how black holes delete information. And all kinds of wonderful things. So check it out on the channel, and see you guys again. Cool, there we go. I feel like I just rambled.